In this last bit of 1103, we're talking about the t-Formulae. They're also known as a Weierstrass substitution after Carl Weierstrass, who came up with them. They're pretty cool, but a little bit tricky to get your head around at the beginning. So in the t-formula, you set t is equal to tan of a on 2. Now, we know our double angle formula is that tan of 2a equals 2 tan a over 1 minus tan squared a. Now we can use that in here as well. If I halve everything here, if I substitute a instead of 2a, I get tan a equals 2 tan a on 2 over 1 minus tan squared a on 2. And as I just said, t is tan a on 2. So what we end up getting is that tan a is equal to 2t over 1 minus t squared. Now that result is very, very, very useful. Let's look at that in terms of a right-angled triangle. So if this angle is A, then our opposite is 2t, and our adjacent is 1 minus t squared. Now let's find the hypotenuse. So the hypotenuse squared is equal to 1 minus t squared squared, this side squared, plus this side squared, which is 2t squared, and that equals 1 minus 2t squared plus t to the 4, expanding that perfect square, plus 4t squared. So let's have a look at what that is. So we've got the 1, negative 2t squared plus 4t squared is plus 2t squared plus t to the 4. Now that's actually also a perfect square. That's equal to 1 plus t squared all squared. That's the hypotenuse squared. So the hypotenuse is equal to 1 plus t squared if I take the square root of each side. Obviously the positive square root because it's a side length. So this is 1 plus t squared. Now we can use that triangle to find values for sine A and cos A. So sine A, for example, is the opposite over the hypotenuse, so it's 2t over 1 plus t squared. And cos A is adjacent over hypotenuse, 1 minus t squared over 1 plus t squared. Now I'm just going to write tan A next to those again as well, even though I've written it above already. That was the opposite over the adjacent. Now those results are on the reference sheet. I did explain that pretty quickly, so you really should go through that in detail yourself, although it is on the reference sheet, as I said, so it's not that big a deal, but it is nice to understand it. So this is just an example showing that rule that I just mentioned. The rule is that tan A equals 2 of tan A on 2 over 1 minus tan squared A on 2. Now what we can see here is that A on 2 is equal to 22.5. So A on 2 equals 22.5, which means A, of course, would equal 45. So this whole thing is equal to tan 45. Now, we could have actually put this in our calculator to cheat because tan 45 is a nice easy one using that exact value triangle, 1, 1, root 2 with 45. Opposite over adjacent, it does just equal 1. And if you put this in your calculator, you will get 1. In example 2, we're asked to prove this identity. Now, to use the t-formula, I'm just going to show that the left-hand side equals something and the right-hand side equals the same thing. So I'm going to work the two sides separately. So the left-hand side is equal to 1 minus cos theta over sine theta. Now, what we saw is that cos theta is equal to 1 minus t squared over 1 plus t squared. and sine theta is equal to 2t over 1 plus t squared. Now what I'm going to do there is I'm going to multiply the numerator and the denominator by 1 plus t squared. We've got this 1 plus t squared in the denominator on both of those, so it makes sense to do that. So 1 plus t squared times 1 is 1 plus t squared, minus this times 1 plus t squared. They're going to cancel out. I'm just going to get 1 minus t squared. And the denominator, the 1 plus t squared, will cancel with the 1 plus t squared, and that's just 2t. Now that equals 1 minus 1, which is 0, plus t squared plus another t squared. So it's 2t squared over 2t. Obviously the 2's cancel, one of the t's cancel, and it's just equal to 2t. Let's look at the right-hand side. So the right-hand side is sine theta over 1 plus cos theta. Again, I'm going to write that in terms of t. So sine theta is equal to 2t over 1 plus t squared, all over 1 plus cos theta, and cos theta is 1 minus t squared over 1 plus t squared. Again, I'm going to do the same trick. I'm going to go times by 1 plus t squared on the top and on the bottom. So I'm not actually changing its value. The numerator, the 1 plus t squared, cancels, and I just get 2t. In the denominator, I've got 1 times 1 plus t squared is 1 plus t squared, plus this times 1 plus t squared, where they cancel, and I get 1 minus t squared. And that equals 2t. And then I've got 1 plus 1 on the bottom is 2, and I've got t squared minus t squared, which is 0. The 2's cancel, of course, and that equals t, which equals the left-hand side. So that's my proof. Okay, in this example, we've got to prove that sec 2x plus tan 2x equals tan of x plus pi on 4. Now, what we can do with this one, because of the 2x, we may want to let t equal tan x instead of tan x on 2. So what that means is that tan of 2x would equal 2t over 1 minus t squared. So I'm just doubling all of those. So sine of 2x would be 2t over 1 plus t squared, and cos of 2x equals 1 minus t squared over 1 plus t squared. So it's exactly the same results, it's just all of these x's are doubled. And that's a really useful thing to do. So the left-hand side is equal to sec 2x plus tan 2x. So sec, third letter c, 1 over cos. So it's this one upside down. So that's 1 plus t squared over 1 minus t squared, plus tan 2x, which is 2t over 1 minus t squared. Now they've got a common denominator, so I can just add them straight away. I'm going to put the 2t in the middle, 2t plus t squared over 1 minus t squared. That numerator we should recognise straight away as a perfect square. That's 1 plus t all squared. The denominator is a difference of 2 squares. So it's 1 minus t, 1 plus t. And of course, one of the 1 plus t's cancels out. So I'm getting 1 plus t over 1 minus t. So that's the left-hand side. Now let's consider the right-hand side. So the right-hand side is equal to tan of x plus pi on 4. So I'm going to use my angle sum formula for that. So remember, tan of a plus b is equal to tan a plus tan b over 1 minus tan a tan b. So let's use that here. So that equals 2. So our a is x and our b is pi on 4. So that's equal to tan x plus tan pi on 4 all over 1 minus tan x times tan pi on 4. Now we will actually see tomorrow a little bit more detail of tan pi on 4, but if you put that in your calculator, put your calculator into radians mode and put that in your calculator, that equals 1. So I'm just going to write the 1 first. I'm going to write 1 plus tan x for my numerator over 1 minus tan x times 1. And that's really interesting, isn't it? Because that's, if we have, we know that t equals tan x, that's what we set it to. So that equals 1 plus t over 1 minus t. And that's exactly what we got for the left-hand side. So that's that proof.